The group that we have for the first panel this morning is going to be discussing their campus cyber infrastructure and network infrastructure and engineering awards. That's the NSF CC NIE awards. We have representation from a handful of places: UC Davis, San Diego Supercomputer, San Diego State University, and Stanford. I'm pleased that Tad Reynales here at Cal IT Squared has been able to bring this team together. We have Matt Bishop. He's a professor in the Department of Computer Science at the University of California, Davis, and he's co-director of the Computer Security Laboratory there. We have Phil Papadopoulos is the director at the San Diego Supercomputer Center, and he's an adjunct professor of computer science and engineering. He's a researcher at Cal IT Squared, and he's also the main architect of the Optoputer and the Quartzite networks. Christopher Paolini is an operating system analyst in the Department of Engineering at San Diego State University. And Johan von Reijendam is at Stanford. He's a network specialist, and he's a member of the Stanford Communication Services Backbone Group in the campus core. At this point, I guess I'd like to have Tad Reynales come up and give you just a little bit of a background on what these awards are about.
Thanks, Mark. So just as a brief introduction, in the last round of awards, there were 6 made to California institutions out of about 36 nationwide, so we did very well. I think a significant factor in that was the fact that we have the CENIC CalREN infrastructure and especially CalREN HPR, which provides something to connect campus cyber infrastructure improvements to, and also to enable access to research collaborators and resources in the state, nationally and internationally. And then explicitly, Lewis Fox provided letters of support for these proposals on behalf of CENIC. So I think that also contributed to our success in a significant way. We invited all 6 of the awardees to participate in this panel. Caltech and USC were not able to join us today because of prior commitments, but they did participate in the CENIC 100 Gig workshop earlier this month, and I believe their slides are available on the CENIC website. I think it's www.cenic.org/workshop. So with that, I'm going to turn it over to Matt Bishop. Each speaker is going to have about 10 minutes, and then Mark and I will probably pose a question or two, and we'll open it up to questions from the audience or the panelists if they want to quiz themselves.
Thank you, Tad. Is this working? Yeah, I guess it is. Okay. Okay, I should start off by saying, in a way, I'm here under false colors. Really, the campus IET, the Information Education and Technology, is driving this. And let's see if I can get this to work. Yeah. One of the concerns, one of the issues that's arisen on our campus is the amount of data that has to be moved around. So the goal of this award, or the work to be done under this award, is to improve the infrastructure so that we can provide the support for the people who are doing large-scale research. Wait a minute. Yeah, that's the right one. I'll get used to this in a minute. Pete Siegel is the person who is in charge of IET, and he's doing most of the work, as I say. The goal is to develop an infrastructure that allows us to move large amounts of data around the campus, and I want to emphasize that. The problem we're having is not with the problem we're having is largely on campus. We'd like to improve, of course, things off campus, and I'll get to that in a moment. But we have several large data projects on our campus. The Large-Scale Synoptic Telescope, which is building a map of the skies over 10 years so that astronomers can analyze it in depth and basically play it back and forth, involves data coming from an observatory in Chile going up to NCSA and then coming onto our campus And when it gets into full swing, the estimate is around 30 terabytes of data a day moving through campus. The Genome Project, of course, everyone knows about the large amounts of data that are involved there. And currently the way it's handled is by mailing hard drives around, which is not exactly convenient. The other aspect of this, which is interesting, is that social sciences uses what they call large data. It's smaller than the typical scientific data sets, but the constraints it functions under are much different. For example, privacy and such becomes far more important. So we're going to have to focus on those as well. And IET and the departments in campus, particularly the research groups, have a history of working together very, very well. So one of the aspects to this work as well is to provide data for a couple of research groups that in turn can feed back information to IET. So a lot of attention was paid to monitoring and providing information that can be used to improve the way the network works. The approach that we're using is simply to get it going quickly. As it's built, people will use it more. And the other goal is to make it as flexible as possible, because currently we have a pretty good idea of what people are using it for, but we don't know how that usage is going to change over the next 5 years or even over the next 2 years. That's one of the advantages of software-driven networking. It makes reconfiguration, rerouting, and monitoring somewhat easier. But in order to maintain the network and in order to get it to continue to function, we want to grow some people who understand how large data works and how the network works and so forth. And since we're a university, undergraduate student assistants would be absolutely ideal for this. The idea is that they will also serve as a bridge to the faculty members and to the research projects to help them make optimal use of the network. The key issues that we see are lie in security and in performance. It's got to meet the needs of the projects that are using the network. And as the needs change, the infrastructure has to be flexible enough to change, hence the advantages of software-driven networking. Also, in terms of security, confidentiality is important for the social sciences, but integrity is critically important for the hard sciences as well. So we need to be sure that the data won't be corrupted as it moves around the network. And we need to control its flow so that if it's to go to one particular group only, that it only goes to that group. This means that we're going to need a network that's available, provides the necessary security functions, and also provides the quality of service that the particular projects demand. And again, all of this will change over time, hence the need for flexibility on the network. Now, here's what the planned architecture looks like. We've got a campus border router hooked up to what we call the Science DMZ, which is really a science network. We have essentially we have an administrative network also, but that's not involved in what we're talking about here. It's got several connections within the university, and also connections going out to the internet through CENIC. And we were able to leverage the roughly $1 million in this grant to get a 100 gigabyte upgrade that's valued at about 1.3 million. So thanks to CENIC and others for that. The idea here is, again, that we can move data quickly within the university and also outside the university. The Science DMZ is really what we call the science network. We want to make that as fast as possible. And one of the issues that we have is we can put in very fast networking between buildings, but in some of the buildings we're running Cat3 wiring. This is not exactly conducive to high speed, to the high speeds we need. So part of what's going on here is looking at upgrading the horizontal wiring within the building. Again, we're upgrading the connection to CENIC, which is our main network provider. And we want to improve the test and measurement capabilities so we know what's going on in the network rather than just making assumptions about what's going on. OpenFlow will give us a lot of flexibility, in particular for the management and for the research. And what we want, too, is to have centralized support for researchers so that the researchers know where to go if there's a question involving networking or if there's some sort of a problem. And we anticipate that the undergraduate assistants will help out an awful lot here. Now, the management structure that we're using basically involves not just IET, which manages all the campus level networks, but also an advisory board made up of people of the community of users who will be using the network. And the idea here is that as the projects need more from the network, they can coordinate improvements to the network and work with IET so that they are able to get what they need. And the improvements will be phased so that people will get the improvements as they need them, but we're not going to try to do everything up front. We want to get something working. We want to get some improvements in there quickly so that people can the projects can begin using those as they come online. The other issue as well is big data is, as you all know, a very hot topic. One of the things we want to do is introduce students to this area. And so the Project Science Board is also going to support students who are working on the network, on performance evaluation, troubleshooting, and things like that. They'll be doing this in conjunction with IET. And so as a result, we'll have a set of people, we'll begin growing people who can work, a body of people who can work with the network and who can improve it and who can help the IET engineers as they do their work. That basically is a cook's tour of what we're planning on doing with the CC NIE grant, and we're very grateful to both NSF and CENIC for all their support. Thank you.
Good morning, I'm Phil. So I want to talk to you about Prism. I think Larry talked to you yesterday in great detail about the application ends of Prism. So I'm going to talk a little bit about the network infrastructure and where we've been and some perspectives. So we had a 100 gigabit per second workshop last week, and I want to put some perspectives on 100 gigabits because we've been through a series of workshops that have been held here. We've thought about 10 gigabit and 100 gigabit and even terabit LANs, and what does that really mean? But it's good to put these things in perspective from a systems point of view. I'm really a systems guy, and you know, if you look at a single stick of 1600 megahertz DDR3 memory today, that's a 100 gigabit per second part, right? So a 100 gigabit per second network is now the speed of a single memory DIMM. If we were to look at nodes on one of our campus clusters that we run over at SDSC, it would take about 2 seconds to drain the memory of that node at 100 gigabits. So not a lot of 100 gigabits is a lot in that perspective. If we look at high performance flash drives, you know, 500 megabyte per second flash drive is a pretty common part today. You can get them on your laptop. You know, they scream. And if we wanted to fill this 100 gigabit per second pipe, we'd want about 24 drives, and we'd have about 8 minutes of content to stream off of those flash drives. And then if we go and look at a high performance file system at SDSC, that's a much larger thing. We have Data Oasis, which is a file system infrastructure that I was critical in designing. It's a 100 gigabyte per second sustained from disk to network. And that runs for about 4.5 days, so that's actually pretty decent capacity. So depending on who you are, you know, 100 gigabits per second is either a lot, it's the whole world, you could never fill it, or it's not so much. And at least at UCSD, we've been here before. We started a project called Optiputer. Larry was the PI of Optiputer. I was a co-PI along with Jason Lee, Tom DeFonte, and Mark Ellisman. And this was before 10 gigabit was everywhere. We got our first 10 gigabit stream connection between here and Illinois, who are primary partners in the Optiputer. We had no idea what to do with it. And these days, it's pretty trivial now for just 2 PCs at each end of that pipe to completely to completely fill it. So in another 5 years, we'll come back and all of us will say, wow, 100 gigabits, it just doesn't look all that big. And then in 2004, so we wrote the optoputer as a large-scale ITR. In 2004, I wrote an MRI with Larry as co-PI to actually make it real, right? So we said, well, we say that networks are getting big. We better build a big network and see what it really does. So this is what that network looked like back in 2005. At the core of the network was a Chiaro Instara router. Chiaro is out of business. There was Juniper T320 at the edge. The T320 is gone. We had just a small number of sites, and each one of those connections that you see were roughly, they were either 10 gigabits or they were multiples of 1 gigabit, just depending on what technology we could get. At the time, the price of a 10 gigabit Ethernet port on the Instara was about $80,000, right? So that was pretty expensive. We now build, we can now build large conglomerations of 10 gigabit Ethernet switches and pay just a few $100s per port for those things. So lots of things changed over the lifetime. On our campus, we're very fortunate here at UCSD that our campus has been forward thinking about putting lots of fiber in the ground, lots of unlit fiber. So it's sort of up to people like us to figure out, well, how do you do it, and how do you do it on the budget of a university researcher? Because everything that you're seeing here is really funded by NSF grant proposal. So we wanted to upgrade that. We wanted to upgrade that network. It went through several variations. The Instara was replaced with a Force 10 E1200, which is still live and running over here in one of the small rooms. Down here is a co-location. So what we have is all this fiber that sort of runs into this particular building and goes out to labs at campus. That device is now about 7 years old, and that was one of the reasons we wanted to write this proposal, and that was replacing the quartzite core. And I didn't put the quartzite core up there. The quartzite core was really packet switch, an optical switch, and a wavelength selective switch, because we were trying to figure out, well, if we were building a campus network of the future, what do we need? Do we need switchable waves? Do we need switchable fibers, or do we just need big packets? And it turns out, just the way technology has evolved over the last few years, that what you really want are really big packet switches, because you can afford to have really big packet switches. So that's what we're doing in Prism, is that this hybrid core that we had in the quartzite MRI is now collapsed down to just a very large packet switch core. And that packet switch it has 10 gigabit capability, 40 gigabit capability, 100 gigabit capability. It will be here hopefully the end of this month, probably maybe no later than the middle of next month. And the small switch has 11.5 terabits per second of bisection bandwidth, which means that it's a very capable switch. We don't really care where things are. We only worry about congestion at the endpoints. There's not congestion inside the switch. If any two ports can talk to any other two ports, and multiply that out, and there's plenty of bisection in the switch to do that. There's also, we want to be able to do expansion to sites off campus, and we wanted to widen the freeway between SDSC and Cal IT2. So you saw this, some of you saw this yesterday, or many of you saw this. Is there a pointer up here, or do I just use my mouse? There we go. Okay, so these are, a number of these sites are already lit, and some other sites are actually coming up and you can see, if you look carefully, that each one of these connections is a different size. Oops, sorry. Page up. There we go. Each one of these is a different size. That's because as we went and did the proposal, we looked at what their current data needs were, and said, okay, that's the size of pipe that they need to get to where they want to go. So the big hitters on campus, the tier 2 LHC cluster in Frank Werthwein's lab over in physics is an 80 gigabit per second connection into the core, as is some experimental stuff to computer science. There's a 120 gigabit per second bridge to to SDSC, and then there are other places around off on our biotech mesa. They don't need bandwidth yet, so we string them at a minimum of 10 gigabits per second, and more if they need it. The switch itself is actually quite expandable. So what does a switch, what do one of these things look like? This is it. It's a Arista 7504. It's their next generation fabric. They make one now, but the updated fabric is what we're getting. That box is 11.5 terabit per second. It's bigger brother. We have two of the bigger brothers with the older fabric at SDSC. Is an 8-line switch, is a 23 terabit per second switching backplane. Cards, you're looking at 48 port, 10 gigabit Ethernet in each one of those guys. We're getting a combination of ports. The next generation supports 48 10 gigabit Ethernet plus two 100 gigabit Ethernet. That's on one line card. Another line card is 36 40 gigabit Ethernet connections. So we're only filling half of the switch, right? Lots of capability. We sort of ran out of money, right? I mean, that's really the way I look at it. But we have lots of capacity, and if we need to, we could pull everything out, all the fabric cards. We could pull out the line cards and put a bigger chassis if we ran out of space, and we ran out of space again. We could put a second chassis in. We could put a second chassis in place. So there's lots of, when you get down to doing this stuff, there's lots of detail that you have to worry about. All of this was actually in our proposal. A combination of copper, short reach optics, long reach optics, and DWDM and CWDM. It just depends on the connection that we're making. For example, we're doing CWDM to computer science building because we're able to use some of the optics that were already existing for some of the computer science projects. For DWDM, we have a lot of DWDM capability from QuartZsite, and we wanted to be able to reuse that, and it's been extremely reliable. I think we've only had maybe one optic failure in 5 or 6 years on DWDM, and no MUX failures, right? These are just passive optical devices. So it's a really nice way to get fiber multiplication without having to go worry about amplifiers and other sorts of things. And then as we're going to 40 gigabit Ethernet, we'll have 40 gigabit both internally and long reach, which is 10 kilometer reach connection over to say physics, right? And to give you an idea, right today this 40 gigabit optic, one optic is about between $5,000 and $6,000. Okay, now that's not too bad if you calculate what it would take you to send 40 gigabit if you were doing DWDM. It's very much on par, but it's sort of all it's all one thing. So really, one thing to pull away from the pieces of technology and the pricing is that it's a little expensive now. It's not that expensive, and the prices are dropping like unbelievably. So if you were to look at a 36-port blade, what we're paying from Arista is somewhere between $250 and $300 per 10 gigabit Ethernet port. Right, so that one blade is 144 equivalent 10 gigabit Ethernet ports. This stuff has gotten very, very inexpensive. So thinking about having lots of bandwidth that is available when you need it and just sort of sits fallow when you don't need it. In that sense, what we've done is we've designed the entire network for burst capacity. So that is one of the big rationale in doing Prism, is that the big data labs on our campus, they're not sending data all the time 7 by 24. When they send it, they need to send it right now, and they don't want to wait. And that's the point of having sort of all this excess capacity. And it's not too expensive to build it. Prism is a $500,000 project. Now, for those of you who are at universities, go run down and figure out how much money you have to bring into a grant to run one $100,000 a year researcher, and you'll look at this and you'll say, wow, we need to save people's time because it's actually precious. So we have built a very high capacity network with the intent that it sort of runs at a few % background, and then when somebody needs to use all of a channel, they get all of that channel as they need it. If we relate this to our campus backbone, so our campus network backbone is a ring of 10 or 20 gigabit. We have a bridge to the campus network. So this is the high capacity network. It bridges for users who are on Prism. It bridges transparently to the campus. we can saturate the campus network. And that's one of the reasons why we've built this network, is to protect our campus infrastructure. You know, you don't want 500 users to completely drown out all the web and email and other such traffic that 50,000 people are on this campus every day actually need. So software-defined networking is not a core piece of this. It's one of the things that we're exploring ourselves, right? We're trying to get our feet wet in running things like Quartzsite. We see the advantages of doing software-defined networking, but we're not quite believers, and we're certainly not disbelievers. And the first thing we have to know whether we're believers or disbelievers is to say, well, we need to get our feet wet with it. And then finally, we have Prism itself has these built-in bridges. They're routing bridges, you know, to the UCSD production network, to exceed resources at SDSU for large-scale computing, to off-campus for high capacity on our biotech mesa, and off-campus meaning it's ready now for 100 gigabit landing that we're getting from CENIC, right? So we're in a sense we're ready to take 100 gigabit now, and then we'll figure out exactly what to do with it. We certainly don't want our network capacity to get in the way of that. And with that, I'm done.
Hi, I'm Chris Paolini from San Diego State, and I'm here to talk to you about our CC NIE award. And what we've been doing is developing a science DMZ network at San Diego State. And so one of the big problems today at universities is that university network operations centers have to support multiple missions. They have to support general networking, web and email. They have to protect people's privacy, financial data and things like that. So they have to implement security infrastructure. Yet the network at universities also has to support data-intensive science. And one of the problems is when people try to do data-intensive science over general-purpose networks, the result is normally very poor performance. And so the problem is when faculty need to adjust the network to support big data initiatives, usually network operations centers are reluctant to do so. They have certain security needs that they have to enforce, and so I always say that security always wins in these kinds of circumstances. And so the problem is when you're trying to do computational and big data research, performance is usually more important than security. However, in terms of general purpose computing at universities, we see that security is thought of more important than performance. And so the big problem is, what can we do today to ensure efficient scientific data transfer between universities and, say, national labs? Now, the solution to this problem is really to implement what's called a science DMZ. And the science DMZ concept was formalized by ESNet, and it's based on the traditional network DMZ. And in the network DMZ, the idea is you separate your protected network infrastructure from internet-facing hosts. And so you take your hosts that have to communicate with the internet, you put them on a separate network, and protected infrastructure where you have databases of financial or personal information, health records, you protect that with a firewall. There's an ability to communicate with the DMZ internally, but you have this protection mechanism here. So it's based on the traditional DMZ model, creating a separate network. Now with the science DMZ, the idea is it really consists of three characteristics. You have to have a dedicated access to a high-performance WAN. You see this through this green pathway. And you have to have high-performance switching infrastructure, something with a lot of buffer, very large buffers to accommodate lossless IP. And then you have one or more data transfer nodes connected to your science DMZ switch. Now the idea here is to separate the general purpose network from your data intensive network. And the idea is you really want to have lossless IP traffic because, as you know, TCP is a very fragile workhorse, and packet loss in TCP is considered as congestion, and whenever there's congestion, the TCP sending rate drops off. And it ramps back up, but even a 1% loss in packet will result in 100 times performance decrease in TCP. So with data-intensive science, if you have to transfer large amounts of data many times, you really need to ensure lossless IP through this high-speed network to your WAN. And that's really the idea of a science DMZ, is to separate your general purpose network from your data-intensive network. Now, to implement a science DMZ using CENIC resources, what you do is you have a EWDM type device. We have a Cisco EWDM at San Diego State. And you can purchase through CENIC an HPR link on one particular wavelength. You can have your Digital California link on another wavelength. And if you have any one-way network connections using an XD network, like we have a direct connection here to San Diego Supercomputer Center, that can be accommodated as well. And the idea is you purchase your own switch. We have a 10 gigabit, a Cisco 4900M, and it's housed at San Diego State University, but it's fully managed by CENIC. So you turn over administrative rights to CENIC. They manage this switch. And then they provide you with one or more LAN handoffs, one for a science DMZ network and one for your general purpose network that goes back to the campus infrastructure. So this is really how you implement implement a science DMZ using CENIC through HPR and a Digital California network. So this is the network that we've set up at San Diego State. This is our EWDM, our Cisco 8-port MUX, and we have a 4900M. This has 8 line speed 10 gig interfaces managed by CENIC. And this has a LAN handoff back to an Alcatel-Lucent OS 10K that we purchased through our CC NIE award. This is our main science DMZ switch. And this provides connectivity to 2 other satellite switches at San Diego State. One goes to our visualization lab that Eric Frost uses. Many of you know Eric Frost at San Diego State. And here you see our Digital California network going back to our main campus general purpose network that's protected by a Juniper firewall. So this is the general idea. This is how you would go about implementing a science DMZ. Now, one thing you can notice about this diagram is we have these perf sonar devices that are attached to each one of the critical DMZ components. And I'll talk about perf sonar in a second. This runs a set of performance and diagnostic tools that allow you to do really real-time bandwidth measurement and notification if things go wrong. So you want to attach a host that's running these perf sonar suite of tools on each one of your critical DMZ components. This slide shows infrastructure that we purchased in 2009 off an MRI award that we got. And this is really our computational science network. This is all 10 gigabit infrastructure that connects to all of our Linux clusters on campus. And these are the data intensive transfer nodes that really sit behind our science DMZ. So this entire network is connected to our Alcatel-Lucent OS 10K switch. And if you notice down here, we have this is our separate CENIC XD network that goes directly from our EDWM over fiber right to SDSC. And this allows us to use trestles and also Gordon directly without having to go through CENIC. So the important features of a science DMZ are high performance data transfer, and we use what's called Globus Online Grid FTP. And we also use the perf sonar suite of diagnostic tools, which I'll talk about. And the other third common feature that all science DMZ should support is the use of a single sign-on name federation system for single sign-on and identity management. I'll talk about that in a second. So really the focus that we use our science DMZ is really for big data intensive science. So at San Diego State we do a lot of ocean modeling. I'm involved in simulation of supercritical CO2 in deep oil reservoirs. We have a lot of scientists doing megagenomics. And so this Science DMZ really supports the ability to move big data sets very quickly to exceed resources without impacting our university general purpose network. Now, the tool that you use to transfer large data sets in between DMZs and from a DMZ to an exceed system is Globus Online Grid FTP. And Grid FTP is based on the traditional FTP, where you have a separate data channel and a separate control channel. The difference is the data channels are in parallel. So this allows you to transfer a file parallelly using multiple flows, TCP flows. And the way it works is on the receiving host, you run a Grid FTP server, and the Grid FTP server receives these parallel flows, and it fseeks to different positions in the file and reconstructs the large file in parallel. So it's really a great tool to move data from in between DMZs or from a DMZ to an exceed host. And one of the really nice features is you can schedule large data set transfers. So you can log on to a command line through a command line interface. You log on to Globus Online, and you can schedule a transfer, say from one exceed to another exceed system and onto your terminal DMZ. Here's an example where you can copy from TAC Lone Star to Trestles at SDSC, and then copy that same file once it's deposited on Trestles back to San Diego State. So you can have any number of these commands. It says SCP here, but that's really just a wrapper. It uses the SCP kind of syntax for transferring, but it's not really a secure copy. And you can see in this graph over here that, you know, almost 60 petabytes of data are transferred every month using Grid FTP. So this is really an excellent resource to use for transferring large data sets. Now, the other key feature that all Science DMZ should support is the use of the Perf Sonar suite of tools. And this is really a collection of diagnostic and bandwidth monitoring tools that you can download. And one of the most important tools is the one-way ping command. And it turns out that congestion is usually one way because routing is asymmetric and can dynamically change. And also, if you're using SNMP to monitor bandwidth problems, congestion can occur very quickly in between your polling intervals. So you really want to use Perf Sonar to do active management. Here's an example of using one-way ping that sends 10,000 packets at 10 millisecond intervals to a remote DMZ. Another really common useful tool is the bandwidth test controller. And this allows you to do, this is really a wrapper around iPerf and NUT TCP and other performance bandwidth tools. This allows you to do parallel bandwidth measuring. Here you can specify, say, a 4 megabyte TCP buffer. And then the third aspect that a Science DMZ should support is really a federated identity management system. And the recommended identity management system that's really being pushed by NSF is In Common Federation. And this is based on Shibboleth, which implements the federated identity providing infrastructure, the open standard by OASIS. And so this tool gives you the ability to delegate to other administrators on campus control over network devices that, say, are attached to your Science DMZ. So if you have a network operations center that really controls federated naming, the network operations center can give faculty members certain administrative rights to other Science DMZ related devices. So this is a very handy tool. You can see the graph over here. Since 2012, there's been, I think it's, 500 universities have adopted In Common Federation as their federated identity management system. So this is highly recommended and really, really encouraged by NSF. Yeah. So if anybody has any questions or wants to contact me about how to set up your own DMZ or have any questions about Science DMZs, this is the people at San Diego State who are involved in this project. We're really thankful for NSF to support this. And some of our current research is We're really involved in looking at developing systems that do compressed sensing from streaming petabyte large data sets that are generated from CO2 sequestration and ocean modeling. And that's one of the big areas of research we're involved in. And in terms of software-defined networking, one of the things we're working on with Alcatel-Lucent, by the way, we chose Alcatel-Lucent at San Diego State because the CSU system, the California State University system, entered into a contract with Alcatel-Lucent, so all network infrastructure for all CSU campuses now is from Alcatel-Lucent. We're working with their application fluent network. That's what they're calling their SDN initiative. And so we're looking at ways to bridge remote DMA traffic between Lustre file systems and 40 and 10 gigabit Ethernet. That's one of the things we're looking at for software-defined networking. Thank you very much. That's all I have.
Good morning. So Stanford was also one of the CC NIE awards awardees last year, and my talk is a little bit more approaching the practical side, and with that I basically want to put the emphasis, understanding that obviously the primary task of IT services for any campus is to make it possible for researchers to do their job, providing their connectivity, all their resources, and so on. But I'm also convinced that this is very difficult if the IT community or the central IT itself, if the central IT itself has difficulty actually providing or managing the services, or the services, the complexity gets so much out of hand, that this also then becomes difficult for us to actually provide researchers with a good service as well. So what made this this award very interesting for us is obviously two main technologies that I want to focus on here is one, obviously software-defined networking. I'm convinced that it can be very beneficial for us on campus. And the other one is the generic term multi-tenancy virtualized clusters or cloud computing. So some of the main things that make it interesting is obviously the software-defined networking promises, promises for now, to be able to give us a lot more control over our network. With that, we mean, I specifically mean, in general, large campuses, what is deployed nowadays is a closed hardware. It's third-party vendor hardware, where functionality and services are basically confined to what firmware will allow you to do. If you really want to become creative with the services that you want to offer to your campus and to your users, it will require a lot of work on your side. You'll have to request maybe added features from your vendors. This may or may not happen. So implementing new services, new tasks, and so on will take a lot of time. Reduced capital and operational expenses is another thing. Hoping that the uptake of software-defined networking will push more commodity switches into the market. So that is also something that specifically the OpenFlow protocol promises, is that with this unified protocol to actually steer or control switches, that as long as a vendor implements this specification, it should not matter too much what type of gear you put in place. You should, in principle, be able to switch out gear from one manufacturer to another without needing to worry about interoperability or loss of functionality or service. With obviously software-defined networking and the ability of taking this functionality and at least most of the intelligence out of the switch and putting it somewhere else on the server, on an application, it now becomes a lot more easy to develop new services. Your services turn into an application. It is one application. It's written in a common language, Java, C, whatever not. And improving on the services, fixing bugs now becomes just an application issue. It doesn't necessarily become a vendor firmware issue or so on. And we also expect this to actually greatly help in simplifying our infrastructure. As most campuses, we have equipment there from different manufacturers. Each have their own interfaces, each have their own management interface. For every new service, you generally need to put in another appliance. And so a common way of managing this infrastructure is usually not really there. There are a lot of opportunities, obviously, for manufacturers to provide this overall management tool. But still, even if this is implemented, it usually does not quite do exactly what you're looking for. The multi-tenancy virtualized clusters, in this case, are more, the interest here lies in obviously, you have all these researchers, many of them put large amounts of their money into actually buying their own equipment for their research, for their calculations and their computes. But this has been increasingly becoming a more difficult issue. Here at Stanford, for us, the research community is fairly independent. People, and I mean, I can't say I'm not guilty of this, but usually people want to be able to keep control over their own equipment. And this gets purchased, this gets put somewhere in their building, in the department, close by, obviously. But these departments are now slowly running out of space. This is not just physical space to put all these kinds of equipment, because you need more and more equipment nowadays with the increase of amounts of data that get handled by researchers. But the buildings run out of power, they run out of cooling. So getting to the researchers to move to a more common infrastructure is definitely a plus point for them. It would save them money. But it's also something that would allow us to provide the growing, to the researchers at least, for their growing needs of compute power, storage, and so on. So there's definitely seems to be some kind of a feeling of moving to this utility supercomputing. Obviously, it does not service every single need, or not necessarily perfectly for supercomputing, but the growing use of virtual machines in the cloud infrastructure definitely seems to be taking off for a lot of companies, and researchers can definitely make use of that. What we also try to think this can provide is obviously an ability for researchers to actually do self-service. Provide them a portal where they can do all their work and allocate their resources, run, and then release them again. So what we've proposed for our infrastructure was we want to build obviously a private cloud infrastructure at Stanford, but one that is tied into our software-defined network infrastructure. And not just at the edge, tied into the software-defined infrastructure, but actually pull the software-defined control all the way into the hypervisor of the clusters. And so for the moment, we're building a somewhat of a prototype environment where we're aiming to build 3 individual clusters distributed across campus. With this, we actually want to be able to look at the possibilities of tying together individual cloud providers or cloud services. And with this comes the deployment of at least about 10 to 15 core switches across campus. So these would be basically providing the backbone of our software-defined network infrastructure. This infrastructure will be obviously providing sliceable resources, not just provide bandwidth and connectivity for researchers and data transferees, but also one of our goals is to actually now build or provide an opportunity for network researchers to actually do at-scale research, where otherwise they would be just limited to what they have in the labs. And obviously, this being a fairly new technology, we definitely think that there will need to be a need for the development of entirely new management tools and for network control as well. Here's a little bit of a logical view of what we're aiming for. building basically a common portal which abstracts basically the control of all these pieces. And we're aiming for something that is very intuitive, specifically because we're also trying to target not just computer-savvy researchers, but also people that are not well-versed in actually using computing infrastructure. You could say the music department, for instance, arts. These are also departments that may be able to actually really contribute to new technologies, new services on the infrastructure. And being able to do that through this intuitive portal would definitely be a help for a lot of that. A couple of these use cases that we're trying to target were specifically, for instance, radar image processing. This case really fits in the cloud computing side, the private cloud. A lot of computing is obviously needed. This need is growing, as mentioned. You have all these public service providers, these public clouds out there which people could be using, but many scientists have not yet actually converted their processes or their computation to a cloud model. For the moment, a lot of them have a couple of desktops or a couple of servers under their desk on which they run their compute, and this is one monolithic program. So with this private cloud infrastructure, we will also want to provide them the opportunity to actually start migrating their services to a cloud format, and then if need be, they can actually then move that off to private or public cloud infrastructures if they need actually more cycles than we can actually provide. Network operations, as mentioned, I think this software-defined networking specifically can provide network operations with a great opportunity of simplifying the network, simplifying the way we manage it, and making, basically freeing up a lot of time and workload to really concentrate on researchers as opposed to just maintaining the current network infrastructure as is, keeping it up and running and so on. This is obviously the primary task, but it takes a lot of the time to do that. So some of the problem issues that we definitely want to target: proliferation of appliances. In most cases, if this is a brand new service that people expect you to deliver, the quickest way to actually deliver this is going to a third-party provider and buying some other appliance, plugging it somewhere in your network. And this appliance obviously needs to generally be inline, because if it's not inline, it doesn't see the traffic. It generally, in most cases, cannot provide a service. This, again, introduces bumps in the roads, delay in traffic. So there's a lack of easy, frictionless bandwidth that researchers are looking for. Added management complexity, obviously, because, again, another management interface is being introduced. Not insignificant part here is the added cost. In general, this is quickly overlooked, although when you look at a piece of equipment or a new service or appliance that you introduce, usually it's 3 times the cost of the appliance at least in services and support that you need to be adding. And keeping that up over the years, it's a significant chunk of the budget that basically gets used there and could be applied somewhere else potentially. So our initial focus is trying to actually, at least for the network operations side, implement firewalls, load balancing, guest access, and some kind of bandwidth of path reservation application on a software-defined network infrastructure. And I'll kind of go quickly through a couple of slides. For instance, firewalls here. Usually this is, in our case, we have about 11 pairs of 10 gigabit firewalls deployed across campus, fronting each one of the departmental networks. So we do not have any at the edge. But that obviously means it needs to be in the path of all your traffic in most cases. And if you look at the way it's applied, most of the cases it's general access list policies. There's not much intelligence there. Limited application layer filtering. And the way we've implemented it, we have a policy basically per department for simplicity, but obviously the number of policies and so on increases. And not only that, but having just one single device that basically handles traffic for 20 to 30 departments, if somebody really hogs the resources on this device, it does go and impact other users and departments. So being able to actually implement a firewall functionality on your network as an application where your switch is a firewall or where any part of your network can basically apply this functionality, I would definitely simplify network, obviously, and eliminate a lot of the bottlenecks. And this is not just for firewalls, but this kind of applies to a lot of appliances out there. Load balancing is another one. We have a number of load balancers out there. Again, this device needs to be in the path of the traffic in most cases. So here, what is load balancing? Really, it is just smart routing. It's just making a smart decision on where you want to send your traffic to a different, to get to your resources and so on. So with software-defined networking, we believe we can actually implement this anywhere in the network, as opposed to needing to co-locate a lot of your hosts in one location behind a actual physical appliance and so on. Guest access is another good one. For the moment, this is a much security through obscurity, IP-based classification in IP tables, and again, it's a bottleneck, a choke point. All your traffic needs to go through that. If you can apply that as an application on top of your network, then again, any place in the network where your traffic hits a switch that is controlled by you, you can now apply this functionality. So you do not need to route your traffic across campus or so to actually get this, this kind of a service in place. Network researchers, very important for us as well, and they are currently limited in their research basically by the fact that they cannot really deploy an at-large, at-scale infrastructure. It costs too much. It would be basically paying twice for an infrastructure because you want it obviously separate from your own to not impact production. But with software-defined networking, we have the ability to actually slice off resources and actually make it possible for them to actually use a slice of the resources across the entire campus network to do this. This is somewhat a little bit of a map of the deployment of the Stanford topology for the moment. We have 5 switches deployed. The other ones will be added, and that will be basically the deployment or the map of the core infrastructure. And we'll start adding multiple buildings to that. We have a couple of buildings tied together already. The computer science department, CIS, which is the EE department, Packard, and Pine Hall, which is the actual network services department. And the way we're deploying it now is, for the moment, we're deploying all these switches, at least the overflow switches, parallel to our actual production infrastructure. For one, actually, to obviously minimize impact for now. Our production infrastructure using a Cisco fabric path topology for the moment. But the idea is to eventually get to a state where you have one set of switches that runs your software-defined networking and where you actually have your appliances and applications implemented right there on these switches, as opposed to needing these appliances that hang off of all the fabric switches or all over your network. So hopefully that's going to simplify stuff a lot and make it a lot easier to actually introduce new services and so on. So we definitely want to involve a lot of students and researchers for that. I think that's it. So thank you.
So we're basically out of time. I'm going to impinge just a couple of minutes on our next set of panels and entertain questions from folks. So if we've got any, yeah, we probably don't have time to have the panelists come up in front for a full set of panel questions, but if we've got anybody that has questions that they would like to ask of the panelists, we'll get a mic to you and then we'll give the panelists a mic. Do we have any questions? Yeah, we've got a question up at the top. Do we have a roving mic? Oh, there's another one.
Yeah, I heard a lot about Arista and Force 10. From Stanford University, what infrastructure are you running? It sounds, I bet you it's Cisco, right? Firewalls and switches?
No, actually, for the moment, our production infrastructure is Cisco, yes. The switching infrastructure is mostly Cisco. Some departments have HP infrastructure. The firewalls are Junipers. Load balancers are F5. But the actual OpenFlow core infrastructure that we're building out now is mostly based on NEC switches. We have a number of NECs and Prontos for the moment. And this is basically mostly chosen because of the capabilities of the switches for the moment. I mean, obviously, we can also deploy OpenFlow functionality on HP switches where needed. But depending on the location where they're used, there may be limitations for that as well.
Thank you. Do we have any other questions? Okay.
So yesterday we heard in the level 3 presentation about the sort of triple threat of security. There's hacking for profit, hacking for a cause, and then government-supported hacking. So what strategies are you employing as we move to 40 and 100 gigabit? The sort of cost of devices or availability is getting prohibitive.
So I think obviously here the solution is no longer having something in the path of your traffic, right? To go and at that kind of speed, I don't think you can check every single packet anymore. So it's going to be something based on exception routing, exception forwarding. So basically building some kind of a trust between endpoints where you can say certain traffic is trusted and you then go and inspect exceptions. Another approach is probably going to be having some kind of a firewall or deep packet inspection device at the edge that you can then route traffic to or forward traffic to, have it inspected. Once it is being declared good or bad, it either gets blocked or you can then from then on fast path it and no longer need to actually send it through deep packet inspection or something.
Okay, thank you. Okay, thank you very much. Let's give these folks an applause.